Okay, let's go over the exam. Hopefully everyone remembered to take the exam. I'd like to go through the exam just to review it real quick, briefly, just to make sure there's no questions about it, and also make sure I didn't make any mistakes when I loaded it in or typed it in. Sometimes there's bugs in the exams. I don't think we had any that I know of this semester. So the first question was, assume the CPU design below has a bug where the wire labeled regwrite-ex could only be driven to the value of 1. Which of the following instructions would no longer execute correctly? So regwrite is almost always 1 because almost all the instructions, at least in lab 3, write to the register file. So all these write to the register file, right? Add-I, mol-h, SLLI, and load up or immediate. They all write a register. The only one that doesn't is the one, not CSRW in general, but the one that writes to IO2, right? So this instruction does not write to the general purpose registers. It writes only to that IO2 out register, right? So this one, you should not have the regwrite EX1 for this instruction. Now, this is a little confusing, though, because if this were a real RISC-V processor, it would have regwrite1 on this guy, right? But this is a hack that we use in this class for our project, where you don't want to write a register whenever the IO address for that guy is F02. Does that make sense? You guys with me? Make sense? What other instructions don't write a register? Well, branches, jumps, store instructions. Of course, we don't have store instructions on our CPU, right? So this is the only one, I think, in lab 3. So it's hard to find an instruction that doesn't write a register. Which RISC-V instruction will multiply the value stored in register 4 by 4? This one is a multiply, so shift left to shift left, and shift left logical immediate, x4, x4, 2. So that's number 1. These ones, by the way...
well, this one you had to select multiple. Those 1 and 3 were both correct.
No, actually, when I looked at it, there was like I clicked both of them, but it marked it half wrong, but gave me full credit. It was really weird.
Well, this one, shift left logical, this is an invalid instruction, right?
SLA.
Shift left arithmetic. I don't think there is a shift left arithmetic, right? Not shift left. Shift left arithmetic only makes sense if the shift amount can be negative. Because if you can have a negative shift amount, then if you shift by a negative amount to the left, you're actually shifting right, in which case the arithmetic might come into play. But if you shift left, you're not shifting an assigned bit.
Yeah.
Okay. So I mean, unless I screwed that up, the only answer should be 1 on that one.
I mean, unless X2, if F2 has 2 stored as the value, number 5.
Oh, yeah, true.
Shift left logical.
Yeah.
X4, X4. If X2's value is 2,
Yeah.
then it would work, but we don't have it.
But we don't know that. Yeah. Yeah, that's a good point. I hadn't thought of that. Yeah. Okay. Moving along, which code is equivalent to the code below? Assign F equals, if x equals 1, then assign F to 2. Otherwise, if x equals 3, assign x to 0. And if x equals 2, assign F to 1. Otherwise, assign F to 3. So what is going on there? What is going on? Anyone know how this one works? So it looks like this is tricky, but we're using a ternary operator here. But it looks like if the input is 0, 1, then the output is 1, 0. If the input is 1, 1, then the output is 0, 0. If the input is 1, 0, then the output is 0, 1. So it looks like we're just, what's the last case? What's the 0, 0? Yeah, so it looks like we're just flipping the bits, right? We're just taking the input and flipping the bits. So the XOR with 1, 1 will do that. I don't think any of these other options work. This one flips the bits, just reverses the order. This one has no effect whatsoever because it's ANDing with 1, 1. And this one is checking to see if they're equal. And if they're equal, it complements. Otherwise, it doesn't complement. But that, I don't believe that works, right? Actually, I guess it would work in this case. And it works in that case. But this one, the first and the third cases wouldn't work out, right? Make sense? Any questions? Okay. When a program is being executed on the three-stage RISC-V CPU, in what stage is the fifth instruction when the third instruction is in write back? If the fifth instruction is in write back, then if the third instruction is in write back, the fourth instruction, which is behind it, would be in execute, right? And the fifth instruction, which is behind that, would be in fetch. So the answer is fetch. Make sense? Okay, assume the following Verilog module. This one just adds 2 numbers, and I'm just asking you to basically fill in the test vectors here. So notice here that C is 2 bits, 3 bits, and A and B are 2 bits, right? Okay, I just noticed this should be 2, right? So this should be 2, but if we add 0 and 0, we should have 0. If we add 0 and 1, we should have 1. So
If you added 2 1s, wouldn't it just have like a 0 in the highest order bit all the time automatically? People don't care.
if you have it, what's that?
Well, because the output's 3 bits and we're adding 2 1 bits, would it just not?
No, it'll be okay because it'll if you add 2 bits, it'll use the carryout to generate a third bit.
Yeah.
The only problem with this is the fact that these guys, A and B, should be marked as having 2 bits, right?
Oh, okay.
Right. So I just noticed that. That's a glitch here. I think what happened here was because this is an image, I updated the question and I didn't update this table, but the idea is yeah, 0, 0 is going to give you 0, 0 and 1 will give you 1, 1 and 0 will give you 1, and 1 and 1 will give you 2. So that's going to be the first option here, right? Matches. But yeah, technically this should be, I'm surprised no one asked about that. That should be 2, these guys should be marked with a 2 bits. All right. Assume the following Verilog module. How many total bits comprise the inputs to module AAA? It looks like just 1, right? Yeah, clock. Consider the RISC-V microarchitecture shown below and assume the following instructions in the corresponding pipeline stage. Which statement is true? ALU source EX must be set to 1. Now remember, ALU source EX would only be 1 if the instruction being executed, which is this guy, is an I type, right? Make sense? But it's, well, it's not an I type, right? LUI is a U type. Now, technically, though, the ALU source could be a don't care, right? Because the LUI doesn't use the ALU, and we don't use the result from the ALU because it gets blocked by this mux, right? So, but it must be set to 0 is wrong. ALU op EX must be set to 1000. Again, that can't be true because LUI is not using the ALU, right? And LUI is in execute. PC fetch contains the address of the instruction in decode EX. No, PC fetch would be the address of the instruction in fetch, right? And reg write EX is set to 1. Well, that would be true because LUI does write to a register. You guys with me? So basically, the way you solve this is when you use the suffix of the instruction to figure out which signal, which instruction each one of these signals corresponds to, and then you just have to ask what that signal should be for that instruction, right? Some of you guys, I noticed in your designs, some of you don't put the suffixes in. It's not a big deal as long as you know what's going on. I think it's helpful though when you're debugging. Most of the signals are in execute though, anyway. Okay, which of the following is a problem with the module below? This one looks pretty good, right? Signal assignment statements have 4 bits on the left-hand side and 3 bits on the right-hand side.
This one's totally free. Because of the if B.
If B.
Yeah, because of B through those double drives.
Yeah.
Well, no, but it doesn't. See, they're both in an always though. It would be double driven if C were driven in another always, right? Or in an assigned statement, or by another structural component, right? But because C is set twice inside of the one always, this is actually just a default output for C in case that if statement isn't fired, right? So that's actually okay. C is double driven, so that's I don't think that's true. There's no structural HDL, that's okay. Blocking assignments are improperly used. No, it's fine. I mean, combinational, you're supposed to use blocking, right? So the problem is 1, the signal assignment statements have 4 bits on the left side and 3 bits on the right-hand side, right? Right, because C is the 4 bits and A and B are 3 bits, and then if you do, the result from this expression and that expression would also be 3 bits, right? You guys with me? Make sense? Okay. Let's see. This one says, what's the value of RD? RD write back. So we're looking at the write back instruction, which is an XOR I. So what is the RD write back? It would be the destination register of the instruction in write back, which is 3, right? Reg select EX. Okay, the EX instruction is an LUI. The reg select for an LUI should be, we're talking about this mux, and we want this mux to have, we want to select input 1 there, right? The input 1 on this mux is the LUI, right? Is the U type immediate. So that should be 1. And reg select write back is referring to the XOR I, and so that one is just going to be 2, right? We're going to send the ALU value through. You guys with me? Okay. Okay, which of the following system Verilog statements takes as input an unsigned 8-bit value and multiplies it by 9? Okay, so this one, how do you multiply a value by 9? You know that if you shift a value by a certain number by n bits to the left, it'll multiply it by 2 to the nth power, right? But 9 is not a power of 2. So you're going to have to, you have to add shifted by 3 bits, the multiply by 8 version, and the multiply by 1 version, right? And if you take the value, multiply it by 8, and you add that to the value multiplied by 1, then you'll have multiplied it by 9. So this one is, A is concatenated with 3 zeros. That multiplies it by 2 to the 3rd power, right? So this sub-expression multiplies it by 8, and this sub-expression just doesn't multiply it by anything, but it 0 pads the left-hand side, so that way both sides of this add have the same number of bits. They don't have to, by the way. I've noticed that in Verilog, you don't have to have the same number of bits on both sides of an add operator. But in this case, I did. I made them equal, and obviously I did that to try to confuse you. But yeah, the answer is number 1. Hey, which of the following system Verilog statements will receive 3 1-bit inputs, A, B, and C, and produce a 1-bit output Y that is true if an even number of its inputs are true? This one actually will work for an odd number because they're XORs, right? So it's not 1, it's 2 adds A, B, and C. If Y is only 1 bit, then if an even number of the inputs are 1, right, an even number would just be 0 or 2, right? So if they're all 0, or if the sum of these 3 is 2, right, then y will be 0, right? So that doesn't work, right? Yes.
Our exam question was if an odd number of its inputs are true.
Oh, did I? Okay. Oh, odd number. Okay, so then it would be 1.
Yeah.
Sorry, I used the wrong version of this question then. Okay, sorry. Odd number. So it's 1.
Yeah.
Yeah, actually,
I was sitting there, I was like, wait, I did the XORs and I was right.
yeah, odd number 1. I think technically, well, if it's odd, would number 2 work too? If y is only 1 bit.
But I think the problem does it would also be 1 and 2 of them, but true. Right?
No, if 2 of them are true, you'd be adding 1 plus 1, you get 2. But then if you store the result only in 1 bit, then 2 would just become 0, right? You'd lose that. You'd lose the carry out.
Yeah.
So I'll have to double check that one because I think 2 is also correct, right? Oh, wait a minute.
But if all three of them were, oh, never mind that.
Yeah. If all 3 were 1, the answer would be 3, in which case y would be 1, yeah. And then I think this one works too, right? This one is also odd number, right? If A XOR B XOR C, right? And this one says if A plus B plus C. In this case, I'm adding 3 1-bits up and comparing it to a 2-bit value, which is okay. You can do that. So this is basically saying if they're all 0 or if the sum is 2, then this would be for an even number, right? So 5. So actually, if the exam said odd, I think answers 1, 2, and 4 are all valid. I mean,
4 basically just doing the exact same thing as 1.
yes, it is. Yeah, it's just written differently. Yeah, so let me double check that, make sure that if you answered, this is question 11, if you answered 1, 2, or 4, that should be correct. Okay, I'll make sure that's the case, and if it's not, I'll make sure that you get credit for any one of those answers. You're sure it was odd, though, right? It was odd. Okay. Alrighty, good. Okay, question 12. The following system verilog code will generate a repeating sequence of n values in consecutive cycles. What's the value of n? Okay, this one is 200-bit signal. It starts as 1. So 200B1 would just put a 1 in the least significant bit of a 200-bit signal. And then it's going to shift it to the left. Actually, it's going to rotate it. It's going to rotate to the left, right? So it's going to shift to the left, and that'll knock off the most significant bit, but then it's going to reinsert the most significant bit into the least significant bit. So it's a rotation operator. So what will end up happening is after 200 cycles, it will eventually become its initial value, right? That 1 bit will get shifted all the way across and then start out at the beginning again. So it's 200, the period of that is 200 cycles, right?
It was on. I just checked again.
It was on? Okay, thank you. Okay, I'll make sure that the right answers are set up then. What input value is below is a don't care? In this case, it would be A bit 2, right? Because A bit 2 is not mentioned in the logic there. And which of the following statements is true? A signal can only be read by 1 block within the same module. 1 always block within the same module. No, it can be read by multiple things. That would be a fan out, right? An always statement is structural HDL. No, it's behavioral. A generate statement cannot include an always block. No, it can. A continuous assignment statement can generate memory. That one is not true. Not true. If statements can be used outside of an always block, not true. Always blocks can be used to design combination logic, true. So it's number 6, right? 6 is the only true statement. Yes?
So in an initial begin and end block, you can use if statements, right, for testing?
Yes.
So is that an always block though?
That's a great question. Initial blocks are basically, they use the same semantics, the same syntax as an always block, but technically, yeah, I should have said initial / always. Yeah, you're right. So that one would mean a generate statement cannot. Wait, which one you were referring to? If statements can be used outside of an always block, so they can be used in initial. So technically, in that case, 5 is true, right? Okay. It's fair enough, yeah. I'll set that up as a correct answer too. So that's Q14, 5. Okay. Yeah, that's a good catch. I hadn't thought of that. Everyone hear that? So the initial block is similar to an always block in that you can use if statements in there, which we did during the test bench lecture. Consider the following module. How many cycles of delay exists between signal A and signal B? I think there's just, this one is A, it takes 1 cycle to make it to delay 1, another cycle to make it to delay 2, another cycle to make it to delay 3. So 3, right? And then B is common. A delay 3 goes right into B, right? So in this case, B is going to change the same time as A delay 3. So A delay 3 and B are going to behave the same here. So it's a 3-cycle delay. Okay, any questions? Yes, question?
So this question, I put 3. It says the correct answer is 3. So it marks it wrong.
Okay, I'll check that too. All right, good. I'm glad we went through this. There's.
Oh, I'm sorry, you marked it right. I'm looking at the question. Sorry.
Oh, okay.
Do you answer question 13?
Yes.
Ours is slightly different.
Yes.
Yeah, ours is, it used A0, A1, and A2, and A3 was our.
Ah, sorry.
A3
Again.
was our, don't care.
So was the answer correct?
Our, yeah, the
Yeah.
answer was correct.
Okay.
Ours
Okay.
is just a little
Yeah.
different.
Yeah. So basically, the idea. So this is an older version of this question, but the idea is that whatever bit isn't used in the logic is the don't care, right? Okay.
Yeah, I think 0, 1, 2.
Okay. Any other questions? All right. Sounds good. Let's move on to the timing analysis lecture. Okay, so last time we were talking about timing analysis, and just to quickly review that, there's in logic there's a delay. Delay is caused by capacitance and resistance. Excuse me. So what that means is if you have a logic gate, there's a difference in time between when the input changes and the output's updated in response to that. So that's the delay through the logic gate, and there's actually 2 delays you have to worry about: the earliest possible delay and the latest possible delay. The earliest is contamination delay and the latest is propagation delay. So a logic gate or a logic circuit will have both a contamination and a propagation delay that defines the range of times you can expect the output to change as a result of the input changing, right? You guys with me? So we said that, for a gate, it's sometimes the pulling the output down to 0 versus pulling it up to 1 may have different delays. And then for a circuit, you have different paths to the circuit. So with a circuit, you have long paths and you've got short paths. The long paths are, or the longest path is called the critical path. And it's the path from the inputs of the circuit out to the output that have it pass through, they have it be subject to the most delay, which is usually defined, is going to be the maximum number of gates it passes through. That's not always the case because you have to calculate it based on the propagation delay of the gates, right? You guys with me? So, yeah, but in this case, we've got A and B pass through 3 gates in series to get to the output, whereas D only passes through 1 gate. And so A and C passes through 2 gates. So A and B to Y is the critical path delay, or as the book calls it, it's the long path. And then the short path is D to Y. You guys with me? Okay. So I mentioned that sometimes the number of paths through a circuit could be quite large depending on how many fan-outs you have. A fan-out is when an output of a gate connects to inputs of multiple gates, right? So then we talked about glitches, which is when you have a case where you change an input and because of the different paths, the different delays of that input through a circuit to the output, you can get a glitch where the output will temporarily change and then change back, right? And so a way to fix that is you can add some redundant logic in here to ensure that whenever you have an input change, it will never leave one Karnaugh map, grouping and enter another, right? So you can fix glitches. There's a way to fix glitches, but you don't always have to fix glitches. And okay, and the reason for that is generally you have the gates inside your circuit, you're going to have data paths in your CPU, meaning that the logic is set up to where the inputs of the logic come from a register, and the outputs from the logic go into a register. You guys with me? So you start with a memory element and you end with a memory element. Okay, and so you've got these are data paths in your CPU. For example, you have your instruction RAM is the starting point, right? Of your say your execute stage, and then the ending point is the register file, right? Or you also have a chance, like for the CSRRW instruction, where your starting point is the instruction, the data passes through the register file, and then you may end up in the register that drives the hex displays, right? So the logic in a CPU is going to be comprised of logic paths that begin with a memory element and end with a memory element. The memory elements are often registers. Okay? So registers have this notion, though, of a setup and a hold time, meaning that the register, like when you think of a register, you think of it as they're edge sensitive. So when there's the clock edge, whatever the input is on that register is sampled during the clock edge, right? During like a really small time as the clock is going from low to high, right? But in reality, and that's fine to look at it that way when you're just doing behavioral design. Like when you're just doing, you're looking at your Quest-to-Sim, when you're designing your circuits. But the real hardware has a requirement that the input to the register, the D, has to be stable for some time before the clock edge. That's called the setup time. And the input also has to be stable for a time after the clock edge. That's called the hold time. And this is a technology-dependent parameter. It depends, the setup and the hold time depend on what technology you're targeting, right? What CMOS technology or what FPGA technology. You guys with me? What happens if you violate that? What happens if you change the D input on a flip-flop between the setup time before the clock edge and the hold time after the clock edge? This is called the aperture time, by the way. The aperture time is the setup plus the hold time. What happens if you change the D input during that time? Well, if you do, there's a chance that the register will become metastable, which means instead of locking in the value of D and freezing it inside the register or the flip-flop, the output will actually go between 0 and 1. Like if your voltage is like, say, 2 volts, the output will go to like 1 volt. And it'll stay there for a while, but not too long, because eventually it'll settle into its correct voltage, right? So the metastability is a temporary thing. You don't want it to happen as long as you make sure that your input is stable within the aperture time. Then metastability won't happen. If it does happen, it causes a problem. It's not catastrophic, but it's a problem. Okay. Okay. So the idea is that when you synthesize the logic onto your FPGA or your ASIC, you want to obey the dynamic discipline, which means that you don't want any metastability to happen, and so you want to guarantee that the input to all your flip-flops is stable during the aperture time. So how do you know it will be? How do you know that's going to be? Well, you have to do a timing analysis or timing closure on the circuit. So basically, the idea is that if you have a register outputting to some logic, and then the output of the logic goes into another register, you want to make sure that the propagation delay of the logic is small enough that the data arrives at the second register before the aperture, right? Before the setup time, right? Makes sense. This is why you can't. This is why it's risky to overclock a chip, overclock a CPU, right? Because you have to make sure that when you're comparing the propagation delay with the clock period time, right? That the propagation delay is small enough with respect to the clock period that it'll be less than the clock period minus the setup time, right? So this is the clock period minus the setup time is your maximum propagation delay, right? So in other words, you don't get a whole clock period to propagate through this logic. You actually get the clock period minus the setup time. Make sense? And if you overclock, then you could get metastability, right? You could violate that dynamic discipline, right? Now, what ends up really happening, though, is when you increase the clock speed of a CPU, you don't just increase the clock speed, you also increase the voltage, right? And when you increase the voltage, the propagation delay will go down with the voltage, right? So if you increase, what ends up happening with the modern CPU is that the clock speed's constantly changing, but when the clock speed goes up, the voltage goes up, right? So that way, if you scale those two together properly, you can still maintain this discipline. You guys with me? Now the voltage, the power consumption of the chip is proportional to the voltage squared, right? So by changing the voltage, you get a huge benefit in terms of power consumption, right? But when you do that, you have to clock it down, as well, right? Did you have a question?
Yeah, when you say change the voltage, do you mean like supply voltage?
Supply voltage, right? Yeah, yeah. But we're not. All we're talking about here, though, is just for a given clock, which is TC. TC is the clock period, which is the reciprocal of the clock frequency. For a given TC in a given voltage, because for a given voltage, the gates will have a propagation delay, right? And a contamination delay. You want to make sure that the propagation delay, the worst case propagation delay, that's the critical path delay, right? The long path has to be less than the TC minus the setup time to make sure that the data arrives in time to be outside the aperture. Make sense? Okay? All right, so, however, there's also a risk that what happens if this propagation delay is really low? What happens if you don't have a lot of logic here? In fact, what happens if you just take this register and connect it directly to that register, so there's almost no propagation delay? What happens then? Then the clock tick comes, right? You get the clock tick, and this guy will output his value, right? And the value will come to this second guy so fast that you may violate the hold time on the second register, right? Because the second register also expects there to be a minimum amount of time where it can expect its input to change on the clock edge. So if I'm a register, clock edge comes, I have to, in order for my hold time to be satisfied, I expect no changes to my input for a little while after the clock edge, right? So if the delay here is too short, that's also a problem because you violate the hold time. So if this delay is too long, you violate the setup time. If it's too short, you violate the hold time. Does that make sense? So you have to make sure that the amount of logic between these two flip-flops or these two registers, it can't be too short, but it can't be too long either. Does it make sense? Okay. So basically the way it works is, as I mentioned, the clock period, which is TC, has to be greater, and this is for the setup time, the clock period has to be greater than or equal to the propagation delay of the logic, right, plus the setup time, right? But also, there's this additional term, TPCQ. That's the propagation delay of the flip-flop. So the flip-flop itself, or the register, has also a propagation delay from the time you get the clock edge to the time its Q output actually changes. There's an additional propagation for that as well. You guys with me? Make sense? So if you add together the logic delay, which is TPD, propagation delay, you add together the delay of this R1 flip-flop. That's the delay relative to its clock. You know, you get an edge of the clock and it takes a while for it to update its Q. So you have to add those together and you have to add the setup time, right? Then needs to be less than or equal to the clock period TC. Make sense? Or as I stated earlier, you can also say TC minus the setup time, right? And additionally, you can subtract the propagation delay of the flip-flop as well, right? And that way, on the right-hand side of this inequality, you have basically three constants. These are constants. These are tied to the technology. The propagation delay of a flip-flop is tied to the technology. You can't change that as a designer or as a compiler or a synthesizer, right? You can't change that. You can't change the clock, assuming you've decided on what clock rate you want to target. And you can't change the setup time because that's a technology parameter. So I've moved all three of those terms, which are unchangeable, to one side of the inequality. And that leaves the TPD on the left-hand side. And that's something you can control because you can play around with your circuit. You can change your circuit. You can engineer your circuit. And if you engineer your circuit, you can change the propagation delay of your circuit, right? How do you do that? Well, you can use like logic minimization, right? Or if you have a really long propagation delay and there's nothing you can do about it, you can break it down into multiple stages, right? You guys in 212, you learned about the CPU has a 5-stage pipeline, right? Did you do the 5-stage pipeline in 212? Did you talk about that? In this class, we use a 3-stage pipeline. So in our CPU, we have a long stage. We have that execute stage, right? It requires you to read the registers and go through the ALU, right? All in one cycle. It may be the case that results in a propagation delay that's just too high. In which case, we may have to break our CPU down into, say, 4 stages or 5 stages. We may have to break that up, right? Now, it turns out in our CPU, it's okay to have that long stage with that long propagation delay because we have a very slow clock, 50 megahertz. But if I told you, I've been toying around with this idea for years. I always thought it would be cool. I just don't think we have enough time. But in this class, if we had a lab where we tried to get your CPU to run at, say, 200 megahertz instead of 50.
Let's overclock the snot out of that thing.
Yeah. Well, you can do that, except you may have to deepen the pipeline if you do that. Because the way the pipeline is set up now, we have that long propagation delay in the execute stage. But anyway, you guys with me on this? Okay, so now there's the hold time constraint as well, where, as I said earlier, you have to make sure the delay isn't too short. And so for that, you have to look at the contamination delay of the circuit, right? So there's a contamination delay associated with the flip-flop. It's called TCCQ. and there's a contamination delay associated with the logic, that's TCD, that has to be greater than the hold time. In other words, we have to have enough delay between the logic contamination delay and the flip-flop contamination delay. There has to be enough delay in here not to violate the hold time of this R2. You don't want this input to change too fast, right? So same thing, this second equation is the same as the first, but it's been reorganized such that the T hold, which is not something you can change, that's on, and the contamination delay of a flip-flop, you can't change those. Those are technology, that's part of the technology library. Those are on one side, but the TCD is on the other side because that's something you as a compiler, as a synthesizer, as a designer, you have power over this, but you don't have power over these two. So these two are constants. This is something that you have to enforce on your circuit, this TCD. You guys with me? And it has to be greater than the difference between these two guys. Does it make sense? Okay, so these are the setup constraint and the hold constraint are constraints on your circuit. Your circuit has to meet those constraints. Okay, so let's look at an example here. So here's an example circuit. So we have, over here, we have the contamination delay of the flip-flops, TCCQ, the propagation delay of the flip-flops, TPCQ, and then the setup and the hold requirements. So these are your technology parameters here. And then we also have the propagation delay and the contamination delay of the individual gates. Now, usually this is different for different gates, but in this example, we're going to say it's the same for all the gates. All the gates have the same contamination propagation. So the question is, is this good? Is this going to work? Is this valid? Is this going to obey the dynamic discipline and not risk metastability? Well, to figure this out, we pretty much have to calculate. Oh, we have a clock too. What's our clock time? Oh, I guess we're allowed to set the clock. We can set the clock to whatever the minimum clock is to try to make this work out, okay? So the first thing we have to ask is, what is the propagation delay of the circuit? What's the worst case path through the circuit? Well, it's going to be these guys, right? A and B to Y prime, right? That's the long path. That's the critical path. So what's that going to be? It's just going to add up all the propagation delays, right? So it's going to be 35 picoseconds times 3, right? Which is like 105, I guess?
Yeah.
105 picoseconds. And then the contamination delay, you have to base this on your short path. So your short path is this guy, D to Y prime, right? So the shortest path here is one gate is 25 pico, right? So the logic TPD and TCD is going to be 105 and 35, right? Picoseconds, I think. Yeah, 25. Oh, sorry, 25 picoseconds. Sorry, the contamination delay is 25, right? All right, so the setup time constraint, if we go back to the equation for that, it says that the clock period has to be greater than or equal to the propagation for the flip-flop 50, so 50, right? Plus the propagation delay for the circuit, which is 105, right? Plus the setup time, which is 60. 60, right? So 50 plus 105 plus 60 is 215. So that is the smallest clock period I can have. That's my limit for my clock speed, right? So that's 4.65 gigahertz. The hold time constraint says that my delay, the contamination of the register, right, which is 30, right, plus the contamination delay of the circuit in between these two is 25. So 30 plus 25 has to be greater than the hold, right? What's the hold? 70, right? So 30 plus 25 has to be greater than 70, which it's not. 55 picoseconds. So this guy, this path is going to update the input to this guy possibly as slow as 55 picoseconds, which will blow away the hold time of this register. So this will fail the hold constraint. Now, luckily, the hold constraint is very easy to fix. What do you do to fix that? You just put additional delays in. So they inserted buffers here. You can insert a buffer just to make this slower. So in this case, I added a buffer here. The buffer presumably has the same contamination delay as any other gate, 25. So if I do that, then my short path now is 25 plus 25 plus 50 plus, what's this guy? 30, so 80, right? So by adding this buffer, I now have an 80. I had to add a buffer here too because this guy also had a 1 gate delay, 1 gate. You guys with me? Okay, so now who does this? Do you do this? No. No, the CAD tool does this. The EDA tool has to do this.
Okay.
Automatically. Okay, so yeah, that works out. Okay, so, but there's some more bad news though about this. The other bad news about this is that the clock is connected to every flip-flop on the chip, which means that you have this huge network, this clock network. The clock network is made of metal, wires. And because it's so big, it has a lot of capacitance. And the clock, when the clock toggles, there's so much metal that not every flip-flop is going to see the clock edge at the same time. So you got the clock comes in and almost like a wave, you know what I mean? Like gates, flip-flops that are closer to the clock pin, the clock source, will see the edge before ones that are farther away. You guys, does that make sense? Every chip has, it's called clock skew. So the problem is that not every, because they're not really, not every gate sees the clock edge at the same time, you have this maximum possible difference called the clock skew. That's the maximum difference in absolute time between any two gates on the chip seeing the clock edge, right? You have to incorporate this into the timing closure, the timing analysis. And you might say, why? Well, because what might happen is, for the propagation delay, if you have two registers, R1, R2, and say R1's clock is running late relative to R2's clock. In other words, R1's rising edge comes after R2's rising edge, right? R1's phase shifted to the right. What that's going to do is that's going to add effectively more delay from R2's perspective, right? Because what's going to happen is when you calculate your propagation delay, the input to this logic is going to be running behind. It's going to be running. So the propagation delay is how long it takes the register to propagate, how long it takes the logic to propagate. But if they both got a late start, that's going to cut into the clock cycle even more, right? So R2 is going to see its input coming in even later than it would be just because of the propagation delay. You guys with me? So you have to build in a margin in your setup time analysis to account for the maximum skew, clock skew. Make sense? Okay, so what that means is that, well, it doesn't really mean a lot. It just means that you have to add that. You have to add that as another term. So the clock period has to be greater than the sum of all the propagation delay plus the setup time, which is how early it has to arrive to meet the setup time, plus the skew, which is, the skew is the maximum amount of time you'll see difference between the clock edge on two parts of the chip. Okay? It's an extra margin you have to build in to account for that. And again, the skew is technology dependent. You can't change that. So that's going to end up together with these other technology parameters, leaving the PD just on one side. So this is going to make it harder to meet your setup time. Also, though, I mean, the skew is worst case skew. So what happens if, I mean, do you really have to still obey the skew if you've got two flip-flops right next to each other? They're probably not going to have a lot of skew if they're close together, right? So this is pessimistic because this skew is usually like the worst possible skew. But the timing analyzer will still consider the worst possible skew. You guys with me? Which means sometimes it'll tell you that your F max, meaning your minimum clock period, you might put this on the FPGA and it'll say, oh, you can run it at 200 megahertz. Sometimes you can bump it up to a little higher, right? But it's risky, right? But the timing analysis is pessimistic. It's trying to guarantee that you'll never have metastability, right? So the FPGA tools will give you the safe number for the clock. Hold time is the same idea, but the opposite. This one's a little confusing. Because in this case, we're doing the opposite thing where R2, his clock is later than R1, the source clock, which means that R1 is going to get a head start relative to R2, which means that if he gets a head start, that means that R2 may get the result even faster than it normally would if all the clocks were synced up perfectly, right? You guys with me? So because the skew may give a head start, you have to also incorporate that in. You have to say that the contamination delay of the flip-flop plus the logic has to be greater than the hold plus the skew, because the skew might give it, again, a head start, right? So you're putting the skew on the same side of this inequality as the hold time, because the hold time is the minimum delay. But you're going to add the skew as a more minimum delay to account for this head start possibility, right? Depending on the phase of the clocks, okay? So, does that make sense? You guys with me? I thought I had an example for that one, but you have to just you have to incorporate the skew into these timing constraints. Okay, but what happens though if you can't enforce the timing constraints? The timing constraints, as I mentioned, are between flip-flop to flip-flop, or register to register, memory to memory, right? Logic in between. But what happens if the input isn't a register? What if it's a button that the user pushes? Then you can't force the user to hit the button at the right time, right? And this happens a lot. In fact, it's not just buttons, it's like network traffic or any I/O for that matter. Anything you can't control, anything the CAD tools can't control, because generally what you'll have is when a network packet comes into your Ethernet card, it's going to get registered. It's going to get captured by a register. That's how it works, right? It samples the data coming through. But it can't predict when that packet's going to arrive. So you may have the packet arrive during the aperture, inside the aperture for the register, and there's really not a lot you can do about that. You basically risk, anytime you have an I/O pin, you risk metastability. You risk the input changing during the aperture, clock edge happens, and then what ends up, the analogy the book has is like, metastability is when you have a ball that's kind of balanced on this peak. And eventually, it's going to fall to one side or the other. These represent 0 and 1, right? But there will be a time that it'll be metastable. And the time it's going to be metastable is a random variable, right? So the way that you model that is probabilistically. You say the probability of the resolution time, that's how long it takes it to get out of metastability. The probability that that is greater than the input t is an exponential distribution. It's e to the negative t divided by tau. Tau is a technology-dependent parameter. It's built into the technology library. So this is something, by the way, you would get from, like, say, the fab. Like if you're fabbing a chip, if you want to tape a chip out and send it over to TSMC to get fabbed. They give you a technology library. This is part of the technology library, right? Or it's part of the FPGA. Like when you guys in Quartus, well, you guys didn't do this because Charles scripted it, but when you go to Quartus and set up a new project, you have to select exactly what FPGA you want, exactly what package it's in, and the speed grade. I don't know if you saw the speed grade.
You do that in 313 pretty much.
Yeah, that speed grade had to do with these timing parameters. Basically how fast the FPGA is, right? The logic. Okay, so the probability that the resolution time is greater than a value t is e raised to the negative t over tau. Okay? So there's an additional parameter here called, that you put, actually there's an additional parameter you put as a coefficient in front of the exponential. It's t sub 0, which is the aperture time, divided by the clock period. So it's just the ratio between the aperture to the clock period, right? How much of the clock period is consumed, is taken up by that aperture time, okay? Okay, so they have this, there's this idea of a synchronizer. A synchronizer is where if you have an I/O pin, and your I/O pin, you don't have, by the way, there's no other choice. You have to, if you have an I/O signal, you got to put it into a flip-flop, right? But in order to reduce the chance that you'll have a bad input value, you can put another flip-flop in series. When you do this, it's called a synchronizer. And the idea is that let's say the first flip-flop goes into metastability. As long as it resolves its metastability before the setup time of the second flip-flop, then we can just use the output of the second flip-flop as our value. You guys with me? So basically the idea is that you expect the first flip-flop is going to periodically become metastable whenever you have an input wire into a logic circuit. But if you put that second flip-flop in there, you can hope that if the first flip-flop goes metastable, it'll resolve itself before the setup time, and then you'll get a clean output on the second flip-flop. Make sense? Okay, so you can calculate then the probability of this whole thing failing as basically what you do is the t value that I gave you before, the resolution time. Instead of just using t, you take the clock period, right? And you subtract the t setup time. And that's the amount of time you have for the first flip-flop to resolve itself before it goes into the second flip-flop. As long as it resolves itself within that period, then the second flip-flop won't be metastable because this input in between will become stable in time. You guys with me? So obviously, if you have a longer TC, this probability will be much better, right? Right, longer. But if your clock is really small, then it becomes more likely that this will fail. Make sense? Okay, so how do you calculate the time between failures of a synchronizer? And again, a failure is defined as when the output of the synchronizer, which is the second flip-flop that's connected in series, goes into metastability. How do you figure that? How do you get an estimate of how often this is going to happen? The number of the probability of failure every second is going to be the number of changes, the number of times the input changes. Now remember, metastability won't happen if you got a button connected to a flip-flop, if no one pushes the button, you're fine, right? Because the only time you risk metastability is if the input is changing during the aperture period. So if you take n equaling the number of changes per second, and you multiply that by T0 over Tc, which is just the coefficient, and then multiply by e to the negative Tc minus T setup over tau, that will give you the probability of failure every second. Make sense? Because again, n is the number of trials per second, number of times you're testing it per second. And then if you just take the reciprocal of that, you get the mean time between failures of the synchronizer. So, so here's an example. So let's say that the clock period is 1 over 500 million, so 500 megahertz, that's a 2 nanosecond clock period. Let's say tau is 200 picoseconds. What does that mean, 200 picoseconds? Well, that, if you guys remember from statistics, did you guys take 590 yet? Not yet? 509? In 509, if you have you probably remember the exponential distribution says that this is the mean, right, is here, right? Right? So the mean is, tau is the mean, essentially. So mean of what? Well, mean of the resolution to the metastability, right? How long it takes. What is the mean of the exponential random variable that tells you how long the thing is metastable, right? So that's why they have, notice it's seconds. Tau is in seconds. 200 picoseconds is tau. And then T0 is 150 picoseconds. What was T0 again? Aperture, right? Aperture time? Okay, and then T setup is 100 picoseconds. And N is 10 events per second. So there's a lot of values here, but you just plug them all in. And what you get is the probability of failure every second is 5.6 times 10 to the negative 6th power, which is, 5.6. Oh, sorry, it's 5.6 times 10 to the negative 5 when you multiply it by 10 per second, right? 10 when you put the n in there, 10 attempts per second. And so if you take the reciprocal of this, you get 5 hours is your mean time between failures, right? Okay. Okay, so we've got, let's see, I've got another example. So here's a quick example that I had on an exam question. Write Boolean logic for the next state function for Q0, Q1, Q2. So this is from the, oh, I don't have the, sorry, I don't actually have the solution on here. So the next state, so the idea here would be that you would have to calculate the propagation and contamination delay for this circuit. So in this case, though, you have to look at, you have 3 flip-flops in here. So you'd have to calculate the contamination delay and the propagation delay between the first 2, right? And the second 2. And then do we have something between this, the third? Let's see, the third flip-flop feeds back into itself. So in this case, you have a path from this guy back to itself, right? So it's not always just two, flip-flop to flip-flop. It can be flip-flop back to itself. You guys with me? So you'd have to calculate that, and then from this, calculate whether this guy meets the setup and hold time. Any questions? Make sense? All right, let's jump forward here. So I have a quiz, quiz 5. It's just 5 questions on this material. Make sure you take that. All right, now let's jump to the next lecture, digital building blocks. Okay, so let's talk a minute about adders. Did you guys cover adders in 211?
Yes.
Okay, so you remember so you had a full adder, which basically a 1-bit adder, right? So you had But a 1-bit adder had 3 inputs and 2 outputs, right? Because there was A and B, which are the 2 bits, and then there was a carry in from the previous column. The carry in is from the adder to its right? The previous bit. And then there's a carry out that goes to the next column to the left, right? Right? Okay, so then, so basically the idea is that if you have an adder, a multi-bit adder, you just associate one full adder with each column, right? With each of the corresponding bits. Okay. Now, the problem with that is, I don't know if you guys talked about this in 211, but the issue with this is that if we look at this in the context of what we just got done talking about, propagation delay, the propagation delay of an adder, this kind of adder, is very bad, right? Because when you calculate the critical path of this adder, the critical path starts with the carry in, and it actually propagates through every column. So the more bits you have, the longer, the slower it is, right? So basically, the propagation, the critical path is essentially from carry in, the first carry in, to the last carry out. And so, what is that? Well, it's pretty simple to figure out. It's just n times the propagation delay of one full adder. You just multiply it. Like if it's a 32-bit adder, it would be 32 times the delay of one full adder. The propagation delay of one full adder. Of course, the full adder itself has got multiple paths in it, right? You guys remember that? Remember, the full adder has I don't have it listed here, but remember the full adder, when it generates C out, it's pretty much a, if there's 2 bits set in A, B, and C, or 3 bits set, then carry out is 1, right? And then if there's an odd number of bits set, then the sum, this is like the exam question, right? If you add up these 3 bits, but the output is just 1 bit, then the sum will be true whenever there's an odd number of 1 bit. So the sum is like an XOR gate, right? But the C out is like a full, you have to do a full sum of products, right? So probably the C out is the slowest part of the full adder, and then you have to multiply that by the number of bits when you make a ripple carry adder. Okay? So that's going to be slow. So what else can we do? How can we make a faster adder? Well, you can use, there's various ways to do that. One way is to use a carry look-ahead adder. And the idea with this is you don't want to have to propagate signals all the way through all these full adders. You want to basically short circuit it and be able to calculate carry-ins faster. So in other words, you still use a full adder, but each full adder, instead of getting its carry-in by passing data all the way through all its bits to its columns to its right, you can pre-calculate the carry-in for each column, right? In other words, it changes how you get carry-ins. Does that make sense? Okay, so the way you do that is there's this notion called generate and propagate. And these are things that you add to the full adder. So each full adder, in addition to having a sum and a carry out, actually you probably would replace the carry out with these. You just have sum, right? But then you can generate a signal called generate, which is true when A and B are both 1. What does that mean? It means that if you have a full adder and you give it 2 1 bits on A and B, you're going to have a carry out regardless of the carry in, right? That's what you're generating a carry out without worrying about any previous bits, any previous columns, right? Propagate, on the other hand, is if A or B is set, you will generate a carry out, but only if its carry in was 1. So basically, propagate means if I have a carry in, I'm going to send a carry out. That means propagate is if propagate is 1, right? If generate is 1, I don't care what the carry in is. I'm guaranteed to give a carry out, right? And so basically, it's very simple. Generate is A and B. Propagate is A or B. Okay. So then the carry out of column C sub I, right? So bit I is going to be basically the generate of I. Forget this part. Just look at this part. It's the generate. I don't know why. This is the logic without using. So basically, I just covered propagate and generate, and yet this guy doesn't use those, right? But we do use them here. So it's the generate of column I, right? Or the propagate of column I if it's combined with the carry out of the previous column. Make sense? Make sense? So this is carry out. This is a little confusing. C sub I. C sub I stands for carry out. Carry out of me, of column I, is a function of the generate of column I and the propagate of column I with the carry out of the previous column. That make sense? Okay. All right, so I think I'm just about out of time, right? Okay, so let's, we'll continue with this next lecture. Don't forget to take quiz 5. Okay, and if you have any questions about the projects, let me know. Okay, thank you.